Welcome back to the deep dive. Today we're looking at a machine that is, I think, the absolute peak of mechanical brutality. We're talking about the cement mixer truck.
It really is. It lives and works in just the dirtiest, hottest, most volatile job site conditions you can imagine.
And that's what makes this so interesting because this is the next frontier for electrification.
It's the ultimate heavy-duty proving ground. I mean, the sheer absurdity of trying to make a high-voltage battery system not just survive, but, thrive for a decade in that environment, that's what makes this such a fascinating deep dive.
And our source material for this is essentially an engineering playbook. It's a very high-level, very rigorous consultancy white paper on how to integrate a 400-volt P2 hybrid system plus an electric power takeoff, or ePTO.
Right, and this isn't just a guide. You called it a playbook, but I'd almost call it a manifesto for survival, a 10-year survival manifesto.
A decade of guaranteed operation in those conditions.
Yeah.
That just seems like an incredible goal.
It means the engineering team has to completely shift their thinking. You can't just use a traditional mechanical design approach.
Right.
It has to be a total system approach.
What do you mean by that? A total system approach.
It means every single decision you make, from where you place a component to what kind of paint you use, has to manage chemistry, physics, and digital controls all at the same time.
All to meet the requirements for power, economy, and of course, the big one, safety standards like ISO 26262.
Exactly. And to get your head around the difficulty, you have to start with a core operational challenge, which is something totally unique to this type of vehicle. The report calls it static high load.
Static high load. Okay, break that down for us.
Well, think about a normal highway truck. When it needs a lot of power, it's usually moving fast, right? So you get all this ram air flowing over the radiators, which helps with cooling.
Sure, power and cooling are kind of proportional to speed.
The cement mixer is the complete opposite. It gets to the job site, it slows down, it idles, it might stop completely on, scorching hot asphalt in the middle of summer.
But it's still working.
It's working its hardest. It needs maximum continuous electrical power to spin that massive drum full of concrete. If it stops, the concrete sets.
So you have maximum power demand with zero cooling airflow.
And that single fact, that one operational reality, dictates absolutely everything else in the design, especially the thermal management we'll get into later.
And that's why this whole deep dive, this whole playbook,
Yeah.
doesn't start with cool design ideas. It starts with the rules.
The non-negotiable standards. This is your admittance ticket to the hybrid club.
Yeah.
You have to get this right before you can even think about anything else.
So let's establish those safety boundaries. We're putting a 400-volt DC system into an environment where, let's be honest, water and conductive cement dust are guaranteed.
It's a recipe for disaster if your safety isn't completely ironclad. So from a regulatory standpoint, the moment you have a 400-volt DC system, you're immediately categorized.
What's a category?
It's called voltage class B. That's under the ISO 64693 standard, and it covers anything from 60 volts all the way up to 1500 volts DC.
And once you're in Class B, a whole new set of rules applies.
A whole new world. The requirements for insulation integrity become, let's say, non-negotiable, because the risk of a fatal electric shock if something fails is very, very real.
Okay, so what's the first line of defense against that kind of failure in a wet, muddy, conductive environment?
It has to be continuous, real-time monitoring. That's the job of something called an insulation monitoring device, or IMD.
It's like a watchdog for the electrical system.
It's the eyes and ears of safety, yeah. It's constantly measuring the resistance path between the high-voltage bus bar and the vehicle's chassis ground. And the rules here are incredibly strict, precisely because you're dealing with things like concrete slurry and mud, which can conduct electricity.
So let's get into the numbers. This is where the engineering challenge really comes into focus. What's the target?
For any DC circuits, the insulation resistance has to stay above 100 ohms per volt.
Okay, so for our 400-volt system,
You do the math, and it means the resistance cannot, under any circumstances, drop below 40 kiloohms.
40,000 ohms. That sounds like a lot.
It is, but you have to remember that number is a moving target. Every microscopic dust particle, every tiny fracture in a wire's insulation, every droplet of water is constantly trying to chip away at that resistance.
So maintaining that 40K ohm number for 10 years after thousands of heat cycles and power washings.
It requires radical over-engineering. You have to build in a massive margin of safety from day one.
And I'm guessing the AC side of the system, the part coming from the inverter, has an even higher standard.
It does. It's even more sensitive. The bar for AC circuits is set at 500 ohms per volt. But the key thing about the IMD is that it has to be an active system.
What do you mean by active? It doesn't just wait for a failure.
Exactly. It's integrated right into the power distribution unit, the PDU, or the battery management system, and it's designed to give you graded warnings.
Like a smoke detector giving you a chirp before the full alarm goes off.
That's a great analogy. For instance, the system might flash a pre-warning on the dashboard if the resistance drops to, say, 150 ohms per volt. That tells the maintenance team, hey, there's a serious problem developing here.
So it gives them a chance to fix it.
A chance to intervene before it becomes a critical safety issue. Then, if it actually hits that fault threshold, that 100 ohms per volt line, the vehicle control unit will automatically limit the power output or even trigger a full shutdown.
That proactive approach seems critical. But what about the worst case scenario? Let's say a catastrophic insulation failure happens inside a big component like the motor. How do you protect the person servicing that truck?
That's the second crucial safety layer. It's called equipotential bonding.
Okay.
What this means is that all the metal enclosures that house high voltage components, the motor casing, the inverter box, the battery box itself, all of them have to be physically connected to the chassis ground.
And not just with a flimsy wire, I'm guessing.
No, with very robust braided straps or heavy gauge cables. The idea is simple. If the insulation inside fails and a live 400-volt part touches that metal casing,
The electricity has a super easy path to follow.
an incredibly easy path. It preferentially flows through that low-resistance ground strap rather than waiting for a person to come along and complete the circuit to ground with their body.
And there must be a specific resistance target for that path, too.
Oh, absolutely. The resistance between any two conductive points on the vehicle and the main chassis ground has to be extraordinarily low. The mandate is less than 0.1 ohms.
Wow.
And those grounding straps, they have to be beefy enough to handle the maximum possible short circuit current long enough for the main fuse to blow. We're talking about cables with cross-sectional areas of 16 square millimeters or even more. This is serious hardware for extreme failure events.
Okay, so let's shift our focus to the battery pack itself. It's this huge, heavy, high-energy vessel bolted to a chassis that's constantly vibrating. This brings us to a big international regulation, ECE R100.
That's right, ECE R100 Revision 3. This is the global standard that governs the safety of the Rechargeable Energy Storage System, or RS.
The RSS being the battery pack.
Yes, and ECE R100 is all about making sure that battery can handle the sheer mechanical abuse of the heavy-duty world. For a cement mixer, that means a brutal vibration test.
What does that involve?
They put it on a shaker table and run a logarithmic sweep vibration test from 7 hertz up to 50 hertz, and they repeat that cycle 12 times. The whole test lasts for 3 hours.
3 hours of constant, broad-spectrum vibration. It's basically simulating years of driving over construction debris, potholes, and, rutted dirt tracks.
It's an endurance trial, absolutely.
Yeah.
And beyond just the continuous vibration, the structure also has to withstand really sharp, acute mechanical shocks. The engineers have to prove, usually with computer analysis, that the mounts can handle high G-force impacts.
Like what kind of G-force?
The standard specifies impacts like 50 Gs over 11 milliseconds. The goal is to ensure that even in a serious accident, this huge, heavy battery pack doesn't detach from the frame and become a projectile.
But the one requirement in ECE R100 that really truly changes how you design a battery, the one that drives these radical material science decisions, is the thermal runaway mandate.
This is the single most critical life safety element in the whole system. As you know, lithium-ion batteries can, under certain fault conditions, experience thermal runaway.
Where one failing cell gets hot enough to trigger a chain reaction in the cells next to it.
A cascading failure. And the ECE R100 standard mandates one thing above all else: containment. After a single cell is forced into runaway for the test, the entire battery pack must not catch fire or explode for at least 5 minutes.
5 minutes? That doesn't sound like a long time, but in an emergency.
It's an eternity. That 5-minute window is designed to give the driver and anyone else nearby enough time to safely get away from the vehicle before a major thermal event unfolds.
So how on earth do you design a system to contain what is essentially a catastrophic chemical reaction and by those 5 minutes?
It takes some really extreme internal engineering, both thermal and structural. We're talking about using very high-performance insulation materials, like thin sheets of aerogel, placed strategically between the individual battery modules.
I slow down the heat transfer from one module to the next.
Exactly, to dramatically slow that rate of thermal propagation. But you can't stop the pressure. As the cells fail, they release a lot of hot gas.
And that gas has to go somewhere.
It has to. So the core solution here is to use directional vent valves. These are specially designed ports that, in the event of a runaway, will open and guide all that high-temperature, high-pressure gas safely away from the vehicle.
You're not venting it onto the cab or onto fuel lines or onto the tires.
Precisely. It's a controlled, managed expulsion of volatile gas, designed to handle the failure gracefully for those vital 5 minutes.
Okay, before we move on to where we physically put these things, let's nail down two last safety boundaries: the Orange Highway and IPXXB.
The Orange Highway is just brilliant in its simplicity. It's an SAE standard, J3344, that says all wiring that carries Class B voltage, so anything over 60 volts, has to be bright orange.
No exception.
No exceptions. It means for a maintenance tech, for a firefighter, for any first responder, that color instantly screams, high voltage, do not cut, do not touch. It's an immediate visual safety boundary.
And IPXXB, that sounds a lot more technical.
It is, but it's just as important for safety. IPXXB protection is all about protecting the service crew. It's a standard that says even when a high-voltage connector is purposefully disconnected for maintenance, the live terminals inside must still be finger-safe.
So a mechanic just going with their job shouldn't be able to accidentally touch a live pin, even with a connector apart.
That's it. It protects against accidental contact with any residual charge that might still be in the system after it's powered down. And that one requirement fundamentally dictates the physical shape and design of every single service connector.
Okay, so we've established the rules of the game. Now for the strategy. Where do you physically place these massive, heavy, heat-sensitive components so they last for 10 years?
This is where the heavy-duty expertise really comes into play. The consultancy playbook is very clear on this. The first rule of layout is you ignore the physical dimensions of the parts. You start with the vehicle's heat map.
You start with the heat.
You have to. In a tightly packed truck chassis, heat is the #1 killer of electronics. So you have to establish rigorous zoning. You identify your hot zones, and you map them against your cold zones.
Let's define that thermal battlefield. What are the parts of a cement mixer that are considered continuous high heat sources?
Well, you've got the obvious ones, like the diesel engine itself, but more specifically, the exhaust after-treatment systems, the DPF and SCR, those run incredibly hot.
Yeah.
Then you have hot hydraulic systems, which can easily be over 90 degrees Celsius.
And the exhaust pipes themselves.
Of course, the exhaust manifold and the pipes can have local hot spots of 120, even 180 degrees Celsius.
That's basically poison for a battery pack or an inverter.
Absolute poison. So the mandate for placing the cold zone components is incredibly precise. The report calls it the engineering red line.
The red line is.
The battery, the PDU, the motor control unit, they're only allowed in the cold zone. And that zone has to be a physical distance of at least 300 millimeters away from any of those continuous heat sources.
300 millimeters.
About a foot.
At a minimum. And the goal is to make sure the ambient air temperature around those components never, ever exceeds 50 degrees Celsius.
The report has a great line here. It says, you cannot use insulation blankets to tough it out. Why is that? Why can't you just wrap the components in a heat shield?
Because insulation only slows down heat transfer. It doesn't eliminate it. Over a 10-year lifespan, that constant, slow-bake heat exposure will prematurely age everything. The plastics, the wiring, the circuit boards. It will lead to power derating and, eventually, failure.
So distance is the only real guarantee of thermal survival. It is. If you try to compensate for a bad location with a blanket, you're just kicking the can down the road. You're sacrificing long-term reliability for short-term packaging convenience.
So this thermal map leads us to the biggest component of all, the battery pack. The report lays out two main options, and it's very decisive about which one is the right choice.
The two options are option A, back of cab, and option B, side rail mounting. And the report emphatically, without any hesitation, recommends option A, back of cab.
Okay, so this is often configured as a vertical energy tower right behind the driver's cab. Let's break down the advantages of that.
The pros are almost all related to longevity and serviceability. First, environmental protection. Putting it up high behind the cab gets it far away from the mud, the road debris, and the worst of that conductive concrete slurry splash zone.
That makes sense.
What else?
Second, serviceability. It's much easier for technicians to access, which is a huge deal for fleet management. And it makes it easier to design for modular or even swappable batteries, which could be a game changer for keeping these trucks in continuous operation. And placing all that weight up front also helps with the fundamental vehicle dynamics problem, right?
Precisely. Regulations require that the front steering axle carries at least 20% of the truck's total weight for safe steering and braking. Putting a massive, heavy battery pack right behind the cab helps shift the center of gravity forward, making it easier to meet that rule.
But of course, hanging a multi-ton battery pack high up on the frame must create its own set of engineering nightmares.
Oh, absolutely. Major challenges. It significantly increases the static load on that front axle, sometimes by 3% to 6%, which might mean you need heavier duty front suspension components,
And it raises the center of gravity.
which has a huge impact on stability. You have to run rigorous tilt tests to make sure it's still safe. And then there's the really tricky part. You have to make sure the cab can still tilt forward for engine maintenance without hitting the battery tower.
So you have to simulate that.
You have to simulate the cab tilt operation combined with the maximum frame twist to check for any overlap or interference. It's a very complex geometric problem.
So if back-a-cab is the recommended, why is the other option, side rail mounting, considered so high risk? It seems like it would keep the center of gravity lower.
It's structurally tempting, but from an environmental and packaging standpoint, it's a nightmare. The side rail is the most valuable real estate on the whole chassis. You've got fuel tanks, air tanks, urea tanks, all competing for that space.
And it's right in the line of fire.
It's the most aggressive mud and debris splash zone on the entire vehicle. To build a battery box that can survive down there and meet the IP69K waterproofing requirement would be incredibly expensive.
Are there other restrictions?
Yes. The truck manufacturers themselves, the big OEMs, they strictly prohibit drilling on the main flange of the frame rail. That's the highest stress area. So that severely limits how and where you can securely mount something as heavy as a battery pack.
So back-a-cab wins because it's the best compromise for safety, protection, and maintenance.
By a wide margin.
Now, even with the best placement, we have to talk about something called the dynamic envelope. The report has this fantastic line: static CAD is a lie.
It absolutely is. This is a lesson that's been learned the hard way many times. You cannot design these systems based on a fixed, static 3D computer model. You have to design for the worst possible moment.
And what is the worst possible moment for a cement mixer?
It's when the chassis is undergoing maximum stress from multiple directions at once. The analysis has to check for the simultaneous combination of events.
Which are?
Full chassis twist, which is typically about plus or minus 3 degrees.
Which happens all the time on a job site.
All the time. Add to that a maximum vertical shock, like hitting a big pothole, which could be a 3G impact. And on top of that, you add the maximum physical deflection of the mixing drum itself as it rotates with a full load of concrete.
You have to model all of that happening at the exact same time.
You have to. And that analysis leads you to a critical clearance red line.
Yeah.
What is the absolute minimum gap you must maintain between any high voltage component and that moving, wobbling mixing drum?
And the number is?
The minimum dynamic clearance must be greater than or equal to 25 millimeters. That's your buffer against chaos. If your static cab model only shows a 10 or 15 millimeter gap,
It's going to hit.
it will rub in the real world. And when a high voltage cable rubs through its insulation against a metal drum, you get a short circuit. Catastrophic failure.
The dynamic envelope is just acknowledging that a truck is a living, breathing, twisting thing. Okay, finally on packaging, let's talk about axle load management. We've added all this weight behind the cab.
Right, so even though it helps meet the 20% minimum, you also have a maximum limit. The engineering constraint is that the front axle static load has to stay at or below 90% of its legal limit.
You need that 10% buffer.
You need that 10% margin for dynamic forces, for braking, for fuel sloshing. So if the battery placement pushes that front axle load up by more than, say, 5%.
Then you have to start moving other things around to compensate.
Exactly. The design then mandates that you relocate other heavy parts, like the fuel tank or the air tanks, further back on the chassis. Or in some cases, you might even have to use a split battery pack to distribute the weight more evenly. It's a constant balancing act.